Okay, well, after much delay, here's Microcontrollers with kingernorth, episode 19. I hope everybody's finding this. This is. Okay, well, after much delay, here's Microcontrollers with kingernorth. There we go, just as I mute the other screen so we don't get too much echoing. This is model train speed with CircuitPython and Arduino. What a mess this has been trying to get going here. So, first of all, let's turn off this starting soon because we are going to start. This is it. Wow, this has taken a while to get here. If you're not getting the chat up, just hit refresh and you should get the chat up. It's now listed as public. So hopefully you've got it going. Make sure you link to it. I don't know why it's giving me such a hassle today, but it has. I had to create a whole new stream for it. I couldn't use my scheduled stream. So here it is. So let's go to our camera zoom and let's have a look at what we're working with today. So I hope you get a chance to see this. I'm not sure where my viewers went to, but my audio seems to be coming through fine. So this is the boards we're playing with today. We have an Arduino Uno and we also have a Feather M4 Express from Adafruit, running CircuitPython on that one and running Arduino on the Uno board. So we're actually doing this in two different languages, and what we're doing is we're creating a speed circuit. And we have a small display here so it can display out to the people that are watching. And what happens is that you can actually read or find out what the scale operating speed of your trains are by running past a couple of LDRs. That's those sensors right down here. These are light dependent resistors, and we've used them before. We used them early on in this setup as well. And basically what happens with this is one gets blocked, the train comes by and it hits the other one, and just with the amount of time I took there, it gave me a scale speed of 9.99 miles per hour. Now this is what happens. This is how it actually works. So what we're doing is we embed these two sensors a certain distance apart, and that distance apart is adjustable to you. The little further away it works, the better. About 6 inches seems to work really, really well. And what we have here is we have it all set up so that we can actually convert that into a miles per hour reading. So I'll just move that again. I'll move across here a little bit quicker, and we see that it is 18.21 miles per hour. And that display comes up for a few seconds, and then it shuts off once the sensors are clear. So if I block this, pick this one up, and I leave my finger there as if it stays blocked, you'll see it isn't resetting, but eventually when I remove my finger, it'll take a few more seconds, about 5 seconds, and then it will reset itself. So that's what we have going here, and this works regardless of which one we do. We can do this one and then trip this one, and we can see it displays as well. What we're going to do is we're going to create the program to make this work. So let's go to our main page, our programming page, and as usual we're going to start with our Arduino programming. So we're going to be starting with a blank page here, but I want to show you the drawings that are involved in this, how to wire this up. Hey, Walter, thank you. I'm glad to see this is working. I'll talk to you later about how much of a nightmare this has been trying to get this to set up. I don't know what's going on with it for sure. Here's our layout of our board. So it's a pretty simple layout in reality. What I have on here is I have my Uno on the left-hand side here. And then what I've done is I've got one LDR here, light dependent resistor, and another one here. I have a couple of 10K resistors in series with them going to ground. I have power going to the other side. So basically what's happened here is I've created a voltage divider. And as this gets blocked or unblocked, the voltage on this green wire coming back to the analog input, and the same thing for the other one, will actually rise or lower. So that's the whole purpose of this. So we'll actually change the voltage coming in on the analog input. And it'll vary from 0 to 5 volts. Ideally, it wouldn't go all the way to 0, and it doesn't go all the way to 5, but it ranges pretty good. And it will depend on the brightness. And then we have our little OLED screen in here. This is the 128 by 64 OLED screen, which is running on I2C, the communication protocol. So the orange and the yellow wires are the protocol attached to the SC L and SDA ports, which are also A4 and A5 on an Uno. And then we've got power, and as you can see by my little jumper here, that should be onto the next pin. They don't obviously go to the same pin. The black goes to the black common rail, the ground. So I guess I should fix that in my drawings for later, but I didn't move it over far enough. Okay, but it is the black wire moves over. And that's what that one looks like. For the Feather M4, it's basically the same circuit. And look at that, I did the same thing on that one too. I drew them to the same spot. That one obviously should be back at the back rail, the red wire. This is the M4. We have our 2 voltage dividers here, so we have a ground coming in. We've got it going to the resistor, back here through the LDR, and then out to power. And the LDRs are there. So just ignore that red wire there. That should be on the other rail. And again, we have 2 sensors, and we have an OLED screen. And they're just connected right to the SCL and SDA are connected to their kind on here. And again, we're just using 2 analog ports on this one. Pretty simple wiring. It's not complicated, but we're going to show you how to set this up. So let's have a look at our Arduino program. As usual, first thing we want to do is we want to go save as, because we're going to make this usable for us. So let's go Files, and we're going to go down here to Save As, and we're going to choose a spot. Oh, that's our downloads folder. That's not going to work. Let's try getting our documents folder, and there's documents. The electronics show. And we're going to come all the way down here to number 19. And you can see I already have some here. So I'm going to call this live underscore Arduino for today. So we're just going to do that. So it's live Arduino. And this is what we're going to be working with. So the first things we're going to do in here is we're obviously going to be putting in some sort of a comment at the top. This is live Arduino by me. Just our normal typical comments for at the top. And this is a demonstration of a speed checker for a model railroad layout. Okay, and this could be modules, this could be a full layout, this could be whatever you want it to be. So that's what that's going to be in here. We're going to have to include our helper files, so we're going to go ahead and grab those from the other file. I'm going to copy and paste them. It saves me a lot of typing on a day like today. We've had enough issues. I don't need more. So we're going to include these helper files for Arduino. What this is going to do, we're going to bring in wire H, which is going to allow us to do the I2C communications. And that's going to allow us to hook up to the OLED screen. And then we're going to add the GFX and the SSD 1306, which is going to allow us to do the printing to the on the OLED screen itself. As for the LDRs, there are no helper files for it. It's strictly for the screen. So with that said, we should probably set up the screen next. So let's go ahead and do that. So I'm just going to jump right in here. And I'm going to paste this in here. And just move it over a bit. So what I have here is I'm going to set up my OLED screen. And I've just put my own comment on here to remind me that SDA is equal to A4 and SCL is equal to A5, so I remember what pins they are. The big things to reset the setup here are going to be the width, the height, and the reset pin. Now, we don't physically wire in the reset pin, but this particular driver, this helper file, requires that we have a reset pin on here. So we end up with the Adafruit SSD 1306, and we're going to call it display. And it's going to have its width, height, it's going to have wire to tell it how to talk on I2C, and OLED reset here. So all of those items are being defined, and those are the 4 parameters that get passed into the helper file, which then lets us talk to the display. So we've done this before, so this is not new, but this is what's going to happen. And then our big things that we want to do after that, we're going to have to set up a pin. And I've actually done a couple of pins here that I'm going to set up. And I'm going to do this in blocks. I'm not going to copy everything over at once, which should prove interesting if I forget something. So what we're going to do is any other pins or variables that we need. So one thing I'm going to do is I'm going to calibrate these LDRs automatically in here. So this is something we haven't done before, but we're going to calibrate them. And that's pin 13. Now pin 13 is pretty simple. It's the built-in LED on the Arduino board. So let me just move this one out of the way and we can zoom in, and that way I can point to things while we're talking about them. So I'm going to turn this, which I know is going to turn the writing in the wrong way. But what I'm going to do is I'm going to zoom in my camera to get a slightly bigger image of everything that's on here. So this should help make it easier just to see. Up here somewhere, underneath here actually, is the LDR pin, or the LED light. That's pin 13, and it's hardwired to pin 13, which is just below that black wire. If I move that over a bit, and we get my fingers out of the way so the light can work. This is tricky without me creating too big of a shadow. There's pin 13. There's the LED almost right beside it on this particular board. It could be anywhere on the board depending on whose board you have, but basically there's going to be a light on here somewhere, and that light is just going to tell you that it's LED 13. It's predefined. It's a standard in most Arduino boards. Not all, but a lot of them have it. And the CircuitPython boards, a lot of them have it as well because people are just used to it, so they put them on. So we're going to use that one. So we're going to use the Calibrate on is going to equal to 13, and then I've got photo 1 is A1, and there's actually going to be a photo 2. So let me just grab that line. We'll copy that, and I'm going to leave a space here because we're going to have other stuff to put in here anyways. So this is going to be A2. So what I have is I'm using A1 and A2 as my two inputs for photo 1 and photo 2, just so I know where they are. So let's move down into our setup file because we want to do some stuff with the setup. And the first thing we're going to want to do with the setup is we're going to want to set up a display, and we're basically going to blank it out. So we're going to do a couple of things here. So let me just grab everything that's involved with the display for setup. And I'm going to bring that over here to the setup file, and I'll get rid of that. So I have to start up the OLED display. So I begin and I turn it on, and this is its I2C address. Now yours could be different depending on whose OLED screen you're working, but mine is 0x3C, and that's its address in hexadecimal. And then we clear the display, which clears it. I set my text color to white, which is going to give me white letters on a black background. If you want to have the reverse, then you would set this to black, and then you would turn on the background color as white, and you could inverse it. Display just tells me to go ahead and display it, and it updates the OLED display, and then I give it a ½ second delay. So that's part of what I'm going to do. The next little part I'm going to add in here is I'm going to add in the serial monitor that we're used to. We've used this many, many times, and the serial monitor is just that. It's serial begin, and what I'm doing here is I'm starting it up so that I can display information, and I'll show you why when we're going to be setting it up. I'm doing this as a debugging tool. I like to be able to get feedback with numbers that I can see what's going on while I'm running it. So if all this is working good, then that's what I do. Let's see, what else have we got here? So pin modes. Well, we're going to have to set the pin mode for calibration. And I'm actually going to copy everything up to where we actually calibrate, and I'm going to bring all that in at once. So there's lots of pieces in here. So let me just add all this. And so what we have here is we did the pin mode, and what I'm going to do is I'm going to set calibrate on as an output. And that's just so I can use that LED and show it as an output pin. Then I'm going to have display, clear display, so I'm going to get rid of anything that's on it again. I'm going to set the text size. This is something we found on the OLED I could do. I could set a text size. 1 to 9 definitely fits within this OLED screen. and you could try other settings as well if you want, but this has got a default text style and it's the size. So we're going to set it to size 1. We're going to give it a cursor position of 25 horizontally, and counting from the top left corner, we're going to go across the top 25 pixels. We're going to come down 30 pixels, and we're going to put in the word calibrating. So we're actually going to display that on the screen, and then the display just tells it to update it. So it's going to display this in text size 1, the word calibrating, and this is pretty small. So I can actually, I think I got enough information here right now. If I verify this, because I can call up the other program and reload it back in, but we're going to build this in stages. So I'm actually compiling. It should say that at the bottom of the screen there. It says compiling. That little green bar will eventually move. There it goes. And it should say that it is compiled. And there we go. It used it up, and it says it used 43% of the program space. If you remember when we were doing this before, we actually only used 6% to create everything that we were doing on the little trinket that we were using, the trinket M0. It just shows you how much more memory that trinket M0 has over the Uno, even though the Uno is way physically bigger than the trinket is. Trinket has way more memory than this one does. So anyways, so this is, I'm going to say that there. I'm going to check my connection on tools here, and it shows it as connected to the Arduino. It says it's Arduino Uno on COM4. So I'm going to go ahead and I'm going to upload this now. So it'll compile. Luckily, once it's compiled once, it tends to compile afterwards a little quicker. And as I say that, it seems to be taking its time. Oh, there it goes. It is a bit quicker. And it's now uploading. And now we should see that on that display, we should see the word ready or calibrating come up. And look at size 1 text is pretty small on here. This is pretty small text. But it does say calibrating, and it fit going all the way across while we were doing that. And actually that LED right there is also on. If I shadow that a little bit, you'll see that that LED is on. That's LED 13. So that's that one I set up here in the code, and I told it to turn cal on to high. So I turned on the LED, it's turned on. So it actually worked, which is really nice. The next thing we want to do is we actually want to go and we want to calibrate both of the photo cells themselves, the LDRs. So I'm going to copy some code. I'm going to bring this in. This is actually quite a bit of code, but that's okay. I'll talk you through it. And here it is here. So what we're doing is we're going to calibrate the LDRs and trigger some set points, because I'm going to need some set points to tell me when they're blocked. But I'm going to do it on the amount of light. Now don't forget, these use ambient light, so if the room light changes, you have to recalibrate them. And you can recalibrate this pretty easy by hitting the reset button or just powering it off and powering it back on. So what I'm doing here is at the top is I'm going to calibrate for a given amount of time. So it says here mils 4,000. So basically what it's doing, while mils are less than 4,000, and basically what that does is from restart time, the internal timer starts to count. And what I've said is all that first part of the code only probably took 2 or 3 mils to operate. And then what's going to happen is for the rest of that time up to 4,000 mils, which is 4 seconds, it's going to do my calibration. What I'm doing here is it's going to just keep repeating this loop and loop and loop until I'm done. And that loop ends down here on rung 51. So it says here photo 1 value is equal to analog read photo 1. And then it says if photo 1 value is greater than photo 1 high, then photo 1 high is equal to photo 1 value. So basically what it does, it takes the highest value that it records during the calibration and saves it to memory. And it saves it to this RAM value called photo 1 value. And that's what we're going to use as our trigger. All right, that's how we're going to calculate our trigger. And actually, Actually, our high will be our setting, but these should be. This should be photo 1 value, and this would be photo 2 value. Now, if you've noticed, I've created a few extra variables here. So I'm going to have to add those. So what we're going to do is we're going to scroll up here to where all our values are, and let's go create some more values in here. This is what I said, we're going to make room because we're going to have to add these. So what I'm going to do is I'm going to add the rest of the files I would need in that area, just to let you know that we're going to have a few in here. So I'm going to copy these. These ones go in here, and I'll explain what all these are in a moment. Just let me get all of these in so I don't forget them. It would be bad if we forget them. So let's see what we added here under photo 1 pin A1. We added photo 1 value. So there it is, the current value of the LDR. And then what we've done is say, hey, what's the high? And we started at 0. That way it's going to get overwritten for sure. No matter what, that value is going to start at 0, and then we're going to take the value. We're going to take the value and write it into the high position. Actually, those other ones were right. It is the saved high that we want. And then we're going to go value 1 set. This is a trigger point we're going to use in a moment. And then we create a couple of Boolean photo 1 enabled and photo 1 home as false. And we do the same thing for value 2. So let me go back down here and let me put these back to where they were. These should be home. My thinking was right before. That's what happens when you jump between doing it at one time and then looking at it at another time. So they are not home. You guys can correct me anytime you want. So there's my auto calibration. Oh, thanks, Walter. Yeah, this is code that works really, really slick, and it's not big. And you can also create this if you really want. And we've done this before. I've done this with Brian. With my friend Brian, is we've taken this code and we've moved it into a subroutine. So we call the subroutine from the setup. And then that way what we do is, because he's at shows often and he's with modules, well, building lighting changes dramatically from the time you set up your modules to the time you're running in the morning to the time you're running in the afternoon, and if it goes to the evening, especially if there's some ambient light from outside that's coming in the building. So you have to recalibrate them every once in a while. And what we've done is we've given it the ability, and what we've added is a recalibrate button. So we can press the button anytime we feel like it, and it triggers this subroutine and it recalibrates them to the new values. So you don't get missed readings on the speed sensors or grade crossings or whatever else you've used these on. On a home layout, you usually only have to calibrate it when you first turn it on, because your light tends to stay the same. You don't tend to have big variations in your light. So an advantage of being in the house as opposed to being on a portable layout. So you just have to take that into consideration when you're doing this. So now what we need to do is we want to do some other last little bit of information here, because I want to know what those values ended up. So I'm going to copy this next set of block of code. Actually, it's a bigger block of code than that. Let me get all of it. And down here, after we've set these values, what I've done in here when I've set on the high value, I'll just paste that in and then we'll look at this. So here, when I create my set points, what I've done is I've taken what is my recorded high value and then multiply it by 70%. So I multiply it by 0.7, which basically makes it 70% of whatever the value was. So it works out really, really well. The next things I do is I update the OLED screen. I clear the display. I set it to a bigger font, so I'm setting it to size 2 this time. I'm going to position 30 across horizontally, 20 rows down, and I'm typing in the word ready. And then I added the display. I want it to update. I also want to send this information to the serial monitor. This is why I said I like using the serial monitor, but I don't use it all the time. In here, I like it during the setup. So what I do is here, I actually take in here and it says set point for photo resistors 1 and 2. So it actually prints that statement up there, and then it says photo set 1 and it gives me a value. Photo set 2 gives me a value, tells me what that 70% value is. And then it says calibration on is set to low. Finally, I turn off this little LED down here, and we're going to see that one go off in a moment and do it. So let's see if I added everything in here. I'm going to do a validate. And then what I'm going to do is I'm going to open up my serial monitor. I'm actually going to upload it, and then I'll open up my serial monitor, and we'll have a look, and we'll see how that works for us, how everything ties together. So that seemed to be happy. So we're going to go ahead and upload this into the board, and we're going to see what happens. Let's give it a try. That's the one thing we can do. It says it's uploading right now. Screen says calibrating, and when it's done, hopefully it's going to say ready, and there it does. It says ready. So it did what it was supposed to do. So let's open up the monitor, which will cause it to reboot. And I'm going to bring that screen in here so we can see it. And there's the message that it's displayed. Now let me just reset this. And actually, if I clear the output, I'm going to reach over and just hit the reset button on the board. It's now saying calibrating. We can see that on the screen, and it says ready, and it says here set point for photoresistor 1 and 2, 655 and 637. So there's my values. It's told me my values, which is really, really handy. So I'm quite happy with that. It actually gave me some numbers, and those numbers are going to range because what we're going to see is the input value on an analog goes from 0 to 1023. So we're actually we're a little higher. We're probably about 2/3 of the way up the scale. Maybe not quite 2/3, maybe a little less than that, maybe 60% of the way up. But it shows us that we've got some good light and we have a good trigger point. So right now it looks good, and this is actually the end of the setup file. We don't have any more to add to that. What we're going to do is we're going to start creating the program now. So in the program, the first thing we have to do is we're going to have to go through a couple of steps here. So what we do is I build this in blocks. And what I'm going to do is I'm going to look at and get my initial reading on the LDRs. So I'm going to break it into smaller steps. So let me copy this, and I'm going to go down here and I'm going to overwrite my loop code, which is just a comment right now. And I'm going to put this in. So what I do in here is my loop. The first thing I want to do is I want to read the current value of the first LDR. So basically what I do is I tell it to take photo 1 value and make it equal to the analog read of photo 1, which is connected to A1. So we're actually going to read in that analog value. Then what we're going to do is we're going to set some Boolean values based on this value. And what we're going to look at, if the photo 1 value is less than the photo 1 set, in other words, it's under that 637 or whatever that number was for that particular one. Let's see here. What was that number? It was 655. So if that number is below 655, then what's going to happen? It's going to say, hey, make the enable true and set 1 home to false. If it's not below, in other words, it's higher, then set photo 1 home as true. So basically what happens here is anytime that this LDR down here in the corner is not blocked, my photo 1 home won't be marked as true. If it does get blocked, it's going to say, hey, it's false, it's being blocked, and it's going to say it's been enabled. And this is going to be the start of my loop of what's going to go on. But before we do that, we don't know which way the train is going to approach these two sensors. We don't know whether it's from this end or the far end. So what we're going to do, actually I think there's going to be one more set of values I might have to put in the up top there. But anyways, let's go and look at the next block of text, of logic. And that's basically going to be reading sensor 2. In other words, instead of saying photo 1 value, we're going to get photo 2 value. So I'm going to come down here And we're just going to put in photo 2 value. And it is the exact same code as photo 1, except everything has set up for number 2. So that's what we've done in here. Then what we have to do is decide, hey, did this event happen like it was supposed to? So if it did, we need to act on that. If one of these get blocked, that means a train is approaching. So we want to go and we want to copy that next set of code. And the next set of code is pretty short. It's another if statement. And what I've got here, it says, basically it says record start time when LDR is tripped. And now it says here, what I've done is I've actually created a multi-state that I'm looking for. So it says if photo 1 enable, or that's what the 2 vertical bars mean. And if you're looking for that, it's the key above the enter key on a PC keyboard. So it's photo 1 enable or photo 2 enable and not start time. Then what I'm going to do down here is I'm actually going to say, hey, start time is equal to mils. So I'm actually going to take the word start time and I'm going to give it a value based on the current clock. So that's like having get current time that we've used in the past. So I'm going to say start time is equal to the whatever the time is internal clock of the Arduino right now, and it's going to record that time. And then it's going to say digital write calibration high on. So I'm going to turn that LED back on to tell me that I'm now in sensing mode. So I'm using that calibration LED not only to tell me when I'm calibrating, but if you're looking at the board, it can also say, hey, I've started recording the time that the train takes to travel from one photo eye to the other. And that's really what that is about. And then what we're going to do is we're going to go down here, and the next block is pretty large, but I need to add in a few more variables to make all this work. So let me find the rest of my variables. Where did we finish? Let's go back up in here and have a look. Let's see, add any other pins or variables that are needed. Okay, I did that. And now what we're going to be doing is we're going to be bringing in a bunch of timer settings. We're actually going to bring in a whole big block of stuff here. So I'm going to bring in some various timer settings. So let me just copy that. And that is going in here right after these variables. Let's have a look at what we have in here. So what I've done is anytime we're dealing with the internal clock, it's a long integer as the data type. So what I've got here is long integer, start time equals 0. So I'm giving it that position as 0. So as long as that's 0, then that would be okay. So what happens is 0 is considered false in logic. So it has the value 0. That's why I can look for the value of start time as being 0, and I say not start time. Because I'm saying, hey, if it's anything but a 0, then okay. But what I'm asking for not that says, is it equal to 0? And yes, it is. Is it false? And it is false when it starts. Then I'm going to have end time, which we're going to do in a moment here. Then I have timer done. I have a reset timer, start, reset current time, and I have a bunch of stuff going on here. And we're going to get into what all that is. So, because that's going to be our next big section. And our next big section is also going to bring in some more variables. Believe me, we're not done with all these variables yet. Let's see, I'm going to go all the way. This is going to be a long block of code because there's a lot in it. Okay, actually there's two parts to this, but I'm going to bring it all in since I have it highlighted. So let me go down here to where our code finishes. I'm going to paste it in, and there's a lot of code there, but let's break it into a couple of smaller parts. So first of all, we did our start time. This is where we just and we turn on our LED. So now it says record end time when the other LED is tripped. So now instead of looking for if photo 1 or photo 2 is enabled, I want to know when photo 1 and photo 2 have been enabled. Don't forget, they get enabled as soon as they're tripped. They don't have to stay tripped. They just, once they're tripped, they are enabled. So once they're both enabled and I have a start time, which means I've recorded my start time in mils, and I have not recorded a timer done yet, it's still false, then I can go ahead and do this next block of code. And there's a lot of stuff inside this if statement, but we're going to break it into a couple of parts. The first thing we do is we create a record of what the end time is. So we had the start time up here. That was when one of the photo sensors were tripped. When the second photo sensor gets tripped, we record the time again, and now we can use that in our calculation because we have a start time and an end time. What we want to know is what that difference is. What was the time between start time and end time? I'm also going to turn off my digital write calibration low. I'm going to turn off the LED because the second sensor was touched. So I'm no longer waiting for that second sensor. So I've turned that LED off. Now we're going to do some calculations here. And we're going to get into this. This is actually a little bit longer, but that's okay. So now what we need to do is, first thing we do is we calibrate the interval time. So I'm going to take the time in seconds, or mils. Actually, it comes in mils, so it's in milliseconds right now. And I'm going to take the end time, which is going to be higher because it was recorded later and the clock is continuous. I'm going to take the end time, subtract the start time from it, and then divide that by 1,000 to give me a value in seconds. So seconds is going to be a floating point number. Way back up here, let me just scroll back up here to where seconds is. Or did we not put in seconds yet? Oh, we didn't add the variable for seconds yet. All right, then let me continue on with this before we do. Okay, we're back down here. Whew. So what I'm going to do is I'm going to create a variable in seconds. And this is going to take that mils. So if it took 1.5 seconds to get from one sensor to the other, that would be 1.5 seconds. And that's what we want. We want the value in seconds. We don't want the value in mils or in thousandths of a second. Then we're going to calculate the miles per hour. And here's the formula. And I put it here as a comment just to let us know. So let's see what it's equal to. It's equal to the distance. The distance is the distance between the sensors, and I'll explain that further, divided by the seconds, in other words, the time. So distance divided by time, times how many seconds are in an hour, times the feet in 1 mile, times the scale of your trains. Because different trains use different scales. There's N scale is a common one for a bunch of people. That is 1/60th of an inch. That's 1/60th scale. In other words, one inch in modeling. If you were to model an inch on the model, that represents 160 inches in the real world. So it's a ratio of 1 to 160. In HO scale, which is very popular, it's 1 to 87. So the scale would be HO, which is 87. Then we end up with O scale. Walter and myself both model in O scale. It's a narrow gauge, but it's still O scale. So it's 1 to 48, so we would put 48 would go in scale. And I'll show you where you do that. So it ends up with this calculation here. So the distance is the distance. That's the distance from the sensor, and that's going to be the distance in feet. Now you're going to say, well, I measure that, but I don't know how to calculate that in feet. Don't worry, I've made it easy for you when we're doing the setup. Time in seconds multiplied by, believe it or not, there's 3,600 seconds in 1 hour. And there's 5,280 feet in 1 mile. So this is where all these numbers fit into it. So that's how our calculation is. Now let's go grab those variables that we need and set them up so I can show you these variables, how they set up in the program. And these are user configurable variables, and I've actually called them that. So a little different than what we've been used to. I'm going to go just above the setup, because that's where these need to be. They're going to go right in here. Now these are user configurable sections. So this is what you change to fit your layout. This little program will work, but you need to adjust these numbers to come up with what you want. So what we have in here is the distance is from one LDR to the other. Distance is in feet, so enter the value in inches. I've made it easy for you here. So what you can do is you can take a ruler and measure from this one to this one. And just basically measure center to center will be fine. It'll be close enough. And what you're going to end up here with, in this case here on this breadboard, it happens to be about 2.25 inches. It's about 2.25 inches. Now, that's why I'm saying if you make them 6 inches apart, you'll even be a little more accurate on your scale. And it allows you to be out by 1/8 of an inch or whatever on your ruler isn't going to make a big difference. 1/8 of an inch is a very small percentage of 6 inches. So this is where more distance is better than less distance. But don't get so long that it's going to take 10 minutes for it to get from one sensor to the other. And you would choose a section of track that's straight that when you enter it, you're going to keep running on it and run through it. So this gives the people an idea of what they're running at on their layout. So this is 2.25 inches. And what I do is I take that inches value and I divide it by 12 inches to a foot. And that distance now is in feet. So that gives me my value in feet that I'm looking for my map. And then here I want you to enter your scale. N is equal to 160, HO to 87, O to 48, S would be, 42, G, F scale, other ones, you can range line L, can be 29. You can end up with all kinds of weird numbers in here, but you just look at the ratio for your scale. TT, I think, is 220. Or no, Z scale is 220. TT's like somewhere in between. So they get all different numbers depending on your scale. So you just put in your scale value here. So in N scale here, it'd be 160. 160. Float time in seconds, that's the time. And these are all floats, so these include decimal points. And miles per hour. So this is all my settings here. So this is the user configurable. You need to put your inches in. You need to put your scale in. The rest of it calculates for you. So really, that's the user-defined variables in here. So you have to set them up for your particular use. So now let's go down to the rest of what was in that big block once we hit the second sensor. Once we've done our calculation, what we want to do is we want to display it on the OLED. So I'm going to clear the display. I'm going to set my text size to 2. I'm going to put my position for the cursor at 35 across and starting at the top row, and I'm going to put in the word speed, colon. Then I'm going to change the text size to 3, make it bigger. I'm going to go to position 20 across, 22 down, and I'm going to put in the actual miles per hour, that calculated value. Then I'm going to go back to size 2. I'm going to go down or across to row 45, and I'm going to go down to row 48, and I'm going to put in the letters MPH. And I'm going to display all of that, and it's going to display on the screen. And then what I also have here is in the serial print, I can print out my distance, the distance and the actual distance, the seconds, the scale, and the scale speed in miles per hour. And then I'm also going to say that my timer is now done. So it only calculates this once for this whole setup. So that's what happens there. Now we do have a little bit more to finish off the program, and I'd like to do that before we download the completed program. So believe it or not, we're almost done. And it's actually just a little tiny bit of code that's left on here to do. And where is it? Let me actually, I guess it's a little more than a tiny bit of code, but let me break it down. It looks like it's 3 little blocks of code yet. Whew. So we'll put in this next block of code. So this is reset once both LDRs are clear. So once the timer is done, so it's done its calculation, and photo 1 is home, in other words, we've come back up above the trigger point. Photo 2 is home, we're above the trigger point, and we have not started the reset timer. Then get the value for mils from the reset timer. and set the reset timer to true. So once this is done, this is only going to happen once, but it's going to wait until it displays it, then it's going to capture the current time of the clock of the microprocessor. So that's what's happening here. The next block of code is going to look after resetting the display. Now, we don't want to reset the display right away. I want to give you a chance to be able to look at it, somebody looking at it on the screen. So I'm going to go and I'm going to copy this, and I'm going to come down here, and I'm going to paste it in. And this is once this reset display, once both LDRs are clear for 5 seconds. So if we've started, the timer has been started, then what we're going to do is we're going to say reset timer current is equal to the mils. So every time it loops through here, it's going to update this current setting. If the current setting is minus the start time, which is up here, is greater than 5,000, in other words, it's 5 seconds or more, then go ahead and do the rest of this. And what we're going to do is we're going to set photo 1 enable to false, photo 2 enable to false, so they're ready to take the next speed reading. We're going to set our start time to 0 to reset it back to 0, which was its starting point. Timer done, we're going to set it to false because we're done with that. Reset timer started, we're going to set to false because we're done with that. So this is all of our big resets in our program. Getting everything back. Hey, there's Brian. Yeah, F, G. Yeah, there's too many scales, isn't there, Brian? There's lots of scales. And then G can vary. Because isn't there 1/124th, and there's also some variations on that too, depending on the Garden Railway. Back to this though. Display, clear display. Set our cursor back down to the 30 rows across, 30 pixels across, 20 pixels down, and type in the word ready, and then display it. So we've updated the display with the word ready again, just like it shows right now on the display. And believe it or not, we have one little last bit of code to finish. Once we've reset all of that, we have one last item to reset. And this actually gets done sooner. So let me go and copy this. We're going to put it down here. The final bit of code. And it says reset the ability to read another speed. And it says if the timer's done and not home or not home, reset timer false. And that's basically the last little bit. Believe it or not, that should be all the pieces. Let me validate this to see if I forgot to copy anything over. I think I got all the pieces this time, unlike last time when I had the problem with it. And calibrating is almost done. It says it's done. So you know what? We're only up to 53% of the program storage. Let's upload this and see how it all works. Let's give this a try. Whew. This is big. So we're going to make sure this is ready. Now, when we're finished uploading, this should go to calibrating. We'll keep our eye on that. It says it's uploading. It's calibrating. Once it's finished calibrating, it should go to ready. And if we look on our screen, there's our new values. 654, 637. Pretty consistent. Looks like my ambient light. It looks like it's a bit cloudier outside. So I lost just a touch of light compared to before. So actually we're going to leave that up here because what we're going to see here is I'm going to block one of these sensors. Number 13 came on. I'm going to check the other one. It now says it's 11.06 miles per hour. And if we check out my display screen here, my distance, 0.19. That is 2.25 inches is equal to 0.19 feet. Seconds, 1.85 from one sensor to the other. The scale was 160, and I better scroll that over so you can see it. And it says here, scale speed miles per hour, 11.06. So I got all of that on my serial monitor, and it did display it there. So let's take another reading. And I'm going to move a lot quicker on these. Whoops. So much for quick. That was really slow. Look at my time in seconds, 5.33. That's because I'm dealing with so much light here for the camera. To keep it happy, I didn't block it very well. There we go, 25.86. And each time I get my new times. That was less than 1 second across those two sensors. And over here it was 25.86 miles per hour. So you can keep doing it. Now this is at 2¼ inches apart. Don't forget, set up that user configurable area. And you're going to set it up to your building. So if you go to put them in and you say, hey, 6 inches isn't going to work here, but 4¾ inches will, then make it 4¾ inches, the distance between the two sensors. And just put it in the user configurable. 4¾ inches would be 4.75. So that will allow you to put it in as a decimal value in there, and it will tell you how many feet that is. And so on with everything else. So your scale, oh, I'm not using 1/60th, I'm using O scale, I've gone to 48. So if we went in here to our user configurable area, let's go up to the top and make some changes. So what we're going to do is we're going to make some changes as if we were making this for another layout. So here's my distance in inches. Let's say I was able to get it, and when I actually drilled my holes and I didn't want to hit my supports underneath, I ended up with 6½ inches long. So I can put in 6.5. And my scale, though, is O scale. So I'm going to change that to 48. So I've made those 2 changes in here. Let's save it. And we're compiling that sketch, and then as soon as it's ready, it's going to upload. And then we're going to see how it affects it. It's uploading it, so let's pull up this screen here. We'll see when the new set points come in. It should be calibrating. There it goes. It's calibrating. When it says ready, it should change. There it is. And we're holding pretty steady on those numbers. So now what I should happen is I'm going to go there and there. That was 11.01. That took a ½ second. That was, like actually that's my distance, sorry. 1.61. Well, you can see it's not that much faster than here, but they're the same speed. That second one's harder to do. There was a really long speed, 3.89. I'm down to that speed. Now I'm going to get down here and I should do that. And there I go. Actually, look at that. Pretty close in time. Let's see if I can do a quick one here. And that should probably be a little quicker than that. That was seemed a little fast. But the math does work out when you work it all out. So that's basically what happens here. So that is how we calculate speed on a model railroad. We've used this. It seems to work. Yes, you're right, Brian, I believe, with the LGB. Started that, but people have varied quite a bit, and there is some differences on what the different scales. I think LGB's been the big accepted one. I know there's a couple other brands out there as well. There's been a lot of different trains over the years, and they all vary, and some of them vary just a little bit, even though they may use the same track. So anyway, so that's how it works. So that's how our big program works. When we were done, how many rungs of code? This is fairly long, but I've added in a lot of comments, left myself lots of room. It's almost a couple of hundred rungs long. It's one of the longest programs we've dealt with on this show, but it works. So what we're going to do is we're going to do one little quick thing here. We're going to go over the CircuitPython version of this. So I'm going to slide that one out of the way. And somewhere or other I have this other one in here, as I triggered the little buttons when I was doing that. And I think I can bring that in one more zoom. There we go. This is the CircuitPython version. So let me call up the code for that. And this is it here. This is the speed test. So this one here, the board is laid out very similar. I'm going to go ahead and block one sensor, block the second sensor, and it shows up there. And actually, LED 13, if you're looking for it, is right up here beside the USB connector. So I block one again, it comes on, and the other one trips off. So it does that. So this is how CircuitPython does their program. So let's have a look at what's involved here. Some of it's easier, some of it's harder. Our overall program is only 166 rungs. It's a little bit shorter, but it does things a little bit different. And let's talk about this. And it's a little change on the OLED display from before, what we did before too. So I had a lot more setup on this one, but the program itself is really short. So I need to bring in all my helper files. So of course I'm bringing in time and I'm bringing in board just like I normally do. Remember, this stuff doesn't preload in, so it has to be loaded in. I have to set up my digital I/O pins because I'm using some, so I have to set those up. Bus I/O sets up my I2C, so I'm using that. Analog input, I'm bringing in analog signals this time, so I need to add those. They're separate from digital. Display I/O, terminal I/O, Adafruit bitmap font, import bitmap font, Adafruit display text, import label, and Adafruit display I/O SSD 1306 is all used for the display. But the display can do more. I can do more with it than what I could on the Arduino, but I can do it at the same time on the Oled, on CircuitPython. CircuitPython draws their stuff differently than it does on Arduino. So the first thing I have to do here is I have to release the displays. So I have to tell it to release any displays that are in memory. It's just a good habit. It's one of those things we need to do. The next what we need to do is we need to set up this I2C communications. In Arduino, we used wire.h, and that took care of the I2C. Yes, when you changed this distance and the scale, you affected the speed. That is correct. So I happen to be hitting around similar times. I used a larger distance, but a smaller scale. I probably should have only changed one at a time, Brian, to show it better. What would happen for the same distances and different scales? But I didn't. So let's get back to this here with the CircuitPython. This one's a little bit more involved. And what I have here is it says create the I2C communications. So first of all, I2C is equal to bus I/O. And it's just setting up the standard pins, the built-in pins. I'm going to use the default pins on the board for my communications. Then it says display bus is equal to display I/O. So there's that display I/O I grabbed from up here. I2D display, I take the I2C communication channel. I set the address for device 0x37. And I think that's the end of that one. That is the exact same display. This is the exact same display that I used on the other one. Exact same style. Then the next thing I set up is I display it with the bus. And basically what happens here is I have to set up the width and the height. So you can see all those values are in there. So it looks like it sets up the bus, which the bus is the I2C and the address. And then I add the height, the width of 128 and the width of 128 and the height of 64. So that's similar to what I did in Arduino, just a different way of doing it. This is where it then varies dramatically from Arduino. Because up until that point, we were still defining that we're going to use I2C, that we're giving it an address to use, that we gave it the width and height of the display. Now it changes quite a bit because of how the fonts are handled with this. This is different than I used the first time when I did the OLED on here, but I only used the factory size of fonts. I didn't do anything special with it. Now I'm getting into some more customization. So what I have to do is I have to create display groups. Now display groups are anytime you flash something up on the screen. So I have one called Speedo, and I have another one called Splash. Splash is the default page that comes up and says calibrating and ready. That's what that does. Speedo is the one that says the miles per hour. That's the display that gives me the miles per hour. So I've created two different screens. This is just like if you had multiple tabs on your computer. I can change from one screen to another. And that's what I'm doing here. I'm also using two different fonts. Now, I actually have to have these fonts built. These are properly built in the proper format. So they take up very little room. And I've got an Arial 12. In other words, it's 12 points in size. And I have Gotham Black 25, which is that big, thicker numbers. It's a bold print, and it's also a little bigger. It's basically twice the size, the font. So this is how I get my other sizes of fonts that I'm using here. Then what I do here is I actually created a bunch of labels. So I actually create a label for the phrase calibrating. And in calibrating, I called it a label. I used the font A12, which is my Arial 12. I've told it to use the text, calibrating. I've told it to use the color, white. And then as I scroll down this line here, I tell it where I want it to display on the screen. I want it to be 24 over from the left edge and down 31, so X and Y coordinates. So where I specify those in set cursor in Arduino, I actually set it when I create the label called calibrating. And then basically I've done the same thing for each of the following. I've created ready in the font A12. I've created speed with the font A12. I created the term miles per hour with the font A12. And then finally I created the actual miles per hour text as the Gotham Black 25. So I've created it in bold print. And I've set where each one of these are going to be located. So those are all the different things they're going to display on the screen. Now I do the initial set. Now I do the splash setup. So this is the splash screen. So what I'm doing is I'm saying color bitmap, display IO, and what I'm doing here is I'm just setting it to the display IO. The bitmap size is the full thing, 128 by 64, and it's a 1. The palette, how many colors are in my palette? 1 color. Palette for position 0, since there's only 1 color, is black. The background sprite for the display is going to be this black color, and it says color bitmap, which I created as the bitmap up top, the full screen scale, and it's equal to the color black, and it starts in position 0, 0. So what I've done there is I've said, take the whole screen, draw me a black box, filled box, 128 wide by 64 high in the color of black. So that blanks out the screen for me. And then I've told it to display show splash. So what it does, it puts up a black box. So it blanks it out so there's nothing there. Then I've set up my speedo screen, which is called speedo append. I'm adding this to the screen called speedo. Remember I created speedo up here, way up here. So anytime I want to add something new to it, I'm going to append to it. I'm going to go and I'm going to enter the speed, the miles per hour, and the text. And that's basically what I'm doing, is I'm adding all those things in there. And that's my miles per hour text. Then I create any required pins, which in this case is my analog pins for 4 and 5 for analog in, and my LED on pin 13. So that's what I've done there. I've created all that stuff. Here's my user scale settings, again, N scale, and my distance in inches, and it converts it to feet. So this is the user settings. I set those up. And then in here I just have all my variables that I need, that I did before, and now I'm going to do my calibration. Calibration's done similar, but just a little bit of difference on them. If you notice, this takes very few lines to write this calibration as opposed to the other one. So here I'm going to turn on my LED. I'm going to turn on the splash screen to say displaying calibrating. So I'm putting that message up. And then what it's going to say here is for I in range, and this is 10,001. What this is saying is it's basically going to count from 1 to 10,000. So for 10,000 times, it's going to sample the values of the inputs, the analog inputs, the LDRs. And it's going to say if it's higher, then take the high value and write it to the word value. And it's just going to keep doing this for 10,000 quick revolutions. Trust me, this is much faster than what it was on the Arduino. We did 4 seconds on the Arduino for calibrating. I think this takes less than 2 to do all of this because it's so fast. Then I set up my set points based on 70%, just like I did before. Then I have a couple of print statements where I could print those out, but because this chip is so much faster, I don't bother turning this on unless I want to turn on the monitor, which is the serial monitor up here, and it'll display it at the bottom of the screen. If I want to check it, I can put that on and it'll put those values up. Then I turn my calibrating LED off. I tell it to clear the screen with my append, and I put up the word ready. So I'm appending that screen So I'm overwriting that same screen all the time. So I've done the splash appends. Now, I get into my main program. My main program is only that long. It's fairly short compared to the other one. But it does the same thing and walks through the same steps. This one might be slightly more efficient than the Arduino code because I wrote the Arduino code first. And then I updated it for CircuitPython. So let's have a look at what's going on here. So this is exactly the same. This is based on the current value. I look at LDR1 and the value is at less than the set point. If it is, turn on enable, turn off home. If it's not blocked, turn on home. But once enable's picked up, it stays picked up as true. I don't reset it with the LDR. Here's the second LDR. Exact same thing. So I did those exact same steps in Arduino. Then it says here, start the internal timer once the LDR is true. So this is what I do. When LDR1 is enabled or LDR2 is enabled and not interval start, then start time is equal to time monotonic. And in this case here, because these are dealing with such small numbers, I actually put in a Boolean value for the intermediate time, and I turn on LED value is true because I'm recording the time to get from one sensor to the other. When I get to the second sensor, I say, hey, if 1 is enabled and 2 is enabled and interval start is true, then it's not at calculate. Then end time equals monotonic. I set my calculate time to true, and I set my LED value to false. I stop reading it. Now I come down here and I actually do the calculation. Look how much shorter this is. This is a lot shorter in the screen. In here, it's if calculate and not calculation done, then its interval time is equal to end time minus start time. Now, one little difference in CircuitPython. CircuitPython is so fast, I could actually end up with a problem where I end up dividing by 0 if both sensors are picked up at the same time. Arduino is not bothered by dividing by 0. Arduino just comes up and just says it's infinity and prints up the letters INF on the screen to tell you it was an infinity. Like you actually got it in the same millisecond. Because this reads in smaller increments than milliseconds, we have to do it differently. It actually reads in seconds, but the decimal places go a lot further than milliseconds. They go all the way down into nanoseconds. So what happens is if you happen to hit the exact same time, so I've said here, if you're less than 1/100th of a second apart, then that's not a valid reading. What I'm going to say is I'm going to, if it's greater than 1/1000th of a second, I'm going to say go ahead and do this. Else, what I'm going to do, instead of putting up infinity, instead of putting up something else, I just put in the numbers 9999. We know it didn't go 999 miles per hour. So that's a false reading. And then what I do, once I do the calculation, I just print it out. This is the format that it uses here. What I've done is I've created this temporary miles per hour text is equal to, and then I've given it a format. And what this does, it tells me it's two numbers, 0.2, which is 2 decimals, so it's a floating point. It tells me it's a float number. It's going to have a decimal in the value. And then it's going to format it, and it's going to grab the value from MPH that we calculated up here. And then it just says display speedo. So it displays all the text that built up speedo, which we did at the top. We built our speedo screen. And it's going to mark the calculation done true. Set current MPC time. So this is current time equals monotonic time. And then what we do here is we do the goal. This is our 5 seconds. So this is basically, we grab in here, we create our reset timer is equal to current time plus 5 seconds. Reset timer is equal to true. And then we come down here and this is all our resets. And it puts us back to our splash screen, which says ready when it's all done. A little bit shorter on this part. I think this was a little more efficient, this code, than the Arduino code in doing the calculation, but it took more setup on the CircuitPython side. It's just a matter of which code you get used to. So if I do this, I'll go there, my red LED's on, I'll do my other one, and it's now 12.21 miles per hour. And you can see the fonts are quite a bit different from each other. I'll do it slower. Do that one. This is going to be a much shorter time, so it's only 5.72. Now let's do one that's really quick. 37.14. Let's see if we can get 999 to come up. I don't know if I can or not. No, but I got 872. Look what happened when my time was extremely short. We got some ridiculous number that shouldn't exist. So it is possible to get some really big numbers in here. And what I'm trying to do is to make sure I just don't get into the false sense that it's going to be, if I divide by 0, because it could be somebody laid something on there, a clipboard, on the layout and went, oh, look at that. Oh, well, it's not going 374 miles per hour on my layout. You may think that when your grandkids come by and they grab the controller and away it goes, or somebody doesn't know how to operate the train, you might think it's going that fast, but it probably isn't. That's going to be more realistic speeds. I got to wait for that. 29.92. And again, this was set for N scale. You could change this again for other ones. Given the same distance, if you go to a slower, if you go to a lesser scale, it should change. So let's go up to the user settings on this one. Let's change that to 48 without changing the distance to the center. Okay, and I'll go save. We'll see it now. It goes through its startup screen. It's going to show calibrating in a moment. There's calibrating. Ready. Look how fast. Actually, it was probably less than a second to do 10,000 intervals of checking the LDRs. Very, very quick. Okay. Now when we do this, that was 4.62. To travel that distance, let's get down 5.88. It's a much bigger scale, so a shorter distance is going to read differently. 8.73. Let's see if we can't get pretty quick speed there. 16.19. But you can see it's quite a bit different than what it was with the N scale. So these relatively work. Having sensors close together are not very good for figuring out the speeds. More distance is better than less distance. So you've got to keep that in mind when you're doing things, is you want to make sure that you set it up for your scale and change those user settings. If you noticed it, when I made a change here, I didn't have to validate and upload. It just did it right away as long as there was no mistakes. If there was a mistake, it would have told me. But it did it very quick. That's one of the advantages of CircuitPython, is the fact that development time is much shorter because I can make little changes and I can flash them up really fast onto the boards. Arduino takes a little bit longer to do it, but more people are used to Arduino. Both are good systems. Both work well. We've gone over our hour on our new scheduled time. I'll see if I can figure out what was happening with the other. I'm glad I was able to get it to stream. I will make sure I go in and edit this and properly paste it onto the site and get rid of all the other stuff that shouldn't be there, all these other streams that lasted that didn't show for some reason or other. And I'm going to have to do some more research to find out why my XSplit and YouTube were having so much trouble, to see who's changed what to make it happen. But anyways, I hope you have enjoyed this. I hope you got to learn something with this coding. I think this is a lot of fun. This is something that can add a nice feature to your layout, regardless of whether you're in N scale, HO, O scale, narrow gauge, standard gauge, whatever you happen to be in. I think this is a nice feature you can add so that people can get an idea. Yeah, thanks for working overtime. Well, it's kind of working overtime. It's just more frustration. You just want to get it done sometimes. You want to make sure you can get through and get the broadcast in. So that's what I did today. We mustered through it. Thank you for attending and sticking with me, guys, for watching the show live. I hope those that get to see it on the playback enjoy it as well. And I think that's going to be it till next time. I have no idea what the next topic is going to be, but it'll be episode 20. 20 since this pandemic has all started. So this is getting to be a lot of shows. All right, so thank you very much. for watching today. I appreciate it. This is kingernorth with my show, Microcontrollers with kingernorth, episode 19, Model Train Speed with CircuitPython and Arduino. Again, I'd like to thank you for showing up. I'd like to thank you for watching this at a later date. You can follow me on Twitter. I will be posting up when I'm doing shows and what's going on @kingernorth on Twitter. Or you can subscribe to the YouTube channel. Go to youtube.com/kingernorth. Turn on your notifications. Make sure you turn on your notifications in your settings as well as on my site. Give me a thumbs up if you enjoyed this. And have a great time. Enjoy.